Hey, in this section we're going to talk about implicit differentiation, and this is really important because now it lets us look at derivatives with equations where x's and y's are just running around all over the place, and in a situation where maybe it's really hard to get a y isolated all by itself. So excuse me, the implicit differentiation looks like this. Find the derivative by treating y as a differentiable function of x and differentiate both sides of an equation with respect to x using the different rules of differentiation, including chain rule. You will have to chain rule everything now, okay? Then we're going to solve for dy dx in terms of x and y together to obtain a new equation that will calculate the slope of a tangent line at any point xy on a graph. So that's a lot of mathematical calculus ease. Let's break it down into what we're talking about. We're talking about taking the derivative of both sides of an equation. And in that case, when we do that, what we're looking at is the derivative of this side right here and the derivative of this side right here, okay? But since that y now, we're going to take derivative of y and it's got a 2 on it, we're going to have to use the chain rule, okay? So if I've got that y squared guy, if I differentiate y squared, so d dx of y squared, okay, then I'm going to do 2 times y to the first power, okay, which is just basically 2y, times dy dx, okay, and this is implicit differentiation, okay, so whenever you have that y in there, you're going to have to take a derivative of the y. What does that look like? Dy dx, that's what it looks like. And then when I take the derivative of the x guy over there on his own, so if I just look at d dx of the x, that's just going to be 1. So what does this problem look like? Well, let's go ahead and write it out exactly what it would look like. On the left-hand side, after I take derivative of both sides, I have 2y dy dx. On the right-hand side, I've got a 1. And what we want to do is we want to find what dy dx is. We want to know what is that thing. So to finish this problem out, we're just going to divide both sides by 2y. And then I've discovered now that dy dx is equal to 1 over 2y. And I now have the equation to find the slope of a tangent line, instantaneous velocity. I know what dy dx is. All kinds of things now I can do from this point, okay? But there's going to be a y in my answer. So if they ask me to find the tangent line at a point, I have to know what x and y are so that I can find the correct tangent line. That's going to be the one big difference on this, okay? So this is really going to open our doors a lot more now for calculus. Let's look at another example on the next slide. Alright, so here are some different things that you can try to remember, or some steps that you can follow whenever you are using implicit differentiation. So anytime we've got y's running around, like a y squared or cubed or a square root or something like that, you're going to use implicit differentiation. Okay, if we have something that just says y equals, then we can just use our normal straight up derivative rules. Okay, but one of the things that we're going to want to do is differentiate both sides of the equation with respect to x. So if you have just a y, if you have just y over here, then when you take derivative with respect to x, it becomes dy dx. Okay, so we already do that. But if you have y squared, we've got to multiply that derivative now with dy dx. Okay, collect all the terms with dy dx on one side of the equation, either on the left or on the right, but get all of those guys together. Okay, then factor out dy dx and then solve for dy dx. So how might that look for us? Well, here we've got a question. Let me move him up just a little bit here. So we've got this question. Find the slope of a circle x squared plus y squared equals 25 at the point 3, negative 4. If we're going to find the slope of the tangent line of the circle, find the slope of the tangent line, then I've got to take derivative. And how do I do that? Well, I'm going to take derivative of x squared. That's going to be 2x. I'm going to take derivative of y squared. So that's going to be 2y, and then derivative of y, dy dx. Okay, and then on the other side of the equation, I'm going to take the derivative of 25, which is 0. Okay? But you've got to remember this. It's really easy to forget that that 0's over there. Okay? Now, that's the first part. So the second part then is to collect all the terms with dy dx on one side. Well, we've got it over here. There's only one term. It's already on the left. Okay? Do we need to factor out? No, but what can we do? We can move 2x from left to right. And so what that's going to give me is, whoops, that's the wrong color, green. What that's going to give me is 2y dy dx equals negative 2x. Okay? And then how do I get dy dx all by itself? I divide both sides by the 2y. And when I divide both sides by 2y, what happens? These guys cancel out. So dy dx is equal to negative 2x over 2y. All right. Now, find the slope. Find the slope of the tangent line at that point. Well, dy dx is my slope. And so if I'm going to find the slope of the tangent line at that point, I'm going to simply take the point that I've been given, this x and y coordinate right here. Here's my x value, here's my y value, and I plug them into my derivative for x and y. So this is going to end up being then negative 2 times 3 over 2 times negative 4. And what is that going to be? That's going to be 3/4. So the slope of my tangent line at the point 3, negative 4 is 3/4. And that's how implicit differentiation works. And oh, by the way, can we write the equation of the slope of this tangent line? You bet. We've already got a point. We just discovered that our slope is 3/4. So we could just go, hey, y plus 4 equals 3/4 times x minus 3. And there you go. That's all there is to it. Implicit differentiation, some steps to follow on a problem that's a little bit complicated, but not too bad. Okay, so here's another implicit differentiation example, and now we're going to look at a little kind of, how this applies in the bigger picture idea. And so we want to show that the slope of dy dx is defined at every point on the curve of 2y equals x squared plus sine y. So notice that we've got y's on both sides. Notice that there's a y inside of the sine, which makes it a little bit tricky. If it wasn't in there, we could maybe solve for y and then take derivative. But since it's inside there, we're going to have to use implicit differentiation. Okay? So what we're going to do is we're going to dive right on in here. We're going to look at the derivative of 2y, and the derivative of 2y is 2 times dy dx. Okay? And then we're also going to look at, on the other side of the equation, the derivative of x squared, and that's going to be 2x, plus the derivative of the sine of y. So the derivative of the sine is cosine, times the derivative of dy dx, or the derivative of y, which is dy dx. Okay, so this is what we've got going on. This is our situation. And notice that I've got dy dx on two different sides of my problem. So I'm going to go ahead and move the green one over to the left, and in the process I'm going to go ahead and change it to the blue color here. So 2 dy dx minus cosine y dy dx equals 2x. So here's my setup. I've got all the dy dx's together on one side. So guess what I can factor out of both pieces? You guessed it, dy dx. So now this is kind of like an algebra problem of old. So I have dy dx times 2 minus cosine y, and that's going to be equal to 2x. And then from there, I'm going to just take and divide both sides by 2 minus cosine y. So dy dx equals 2x over 2 minus cosine y. Okay, so what we want to do is we want to show that the slope is defined at every point. Well, the only place we're not going to be defined is where we get 0 in the denominator. Okay, right here. Where are we going to get 0 in the denominator? And we only get 0 in the denominator when the cosine is equal to 2. Well, guess what? The cosine always bounces between 1 and -1. So there's no way that we're going to get a 0 in this denominator. And since there's no way we can get to 0 in this denominator, we can say that 2x over 2 minus cosine y is defined at every point. Alright, so in this example what we're going to do is we're going to wrap up this part by taking derivative of the equation of an ellipse, and not only that, finding a normal line and a tangent line at a specific point. Okay? Sounds tough. It's not bad. Here's the deal. When they give us a value for x and a value for y, they're giving us two critical pieces of information that we're going to have. Because when we take a derivative of an ellipse, we're going to have a y and an x value running around. We need a spot that's on the graph, not some random place like on a quadratic function or a linear graph that rolls through almost every value of x. There are values of x that aren't used, and we cannot find a derivative at those places. So when they ask you to find the normal and the tangent line to an ellipse, they will give you the values that they want to use, and it should be a value that should be on the ellipse. So you shouldn't have to check, but every now and then you might just make sure. Okay. So what we're going to do with derivative on this guy is, notice we're going to have derivative here, we're going to have derivative here, we're going to have derivative here, but right here in the middle we have a u and we have a v. So we're going to have to use the product rule on this guy. Okay, and you'll be all right, but you just have to pay attention. So let's dive in. The derivative of 2x squared is 2x. Okay, the derivative of x times y is the first times the derivative of the second, and in this case the second part is that v, and that's just y. So the derivative of y is dy dx. Plus the derivative of the first, which is that x, times the second, which is the y. So he actually turns out to not be too bad. Okay, plus the derivative of y squared. Well, that's going to be 2y times the derivative of y, which is dy dx. And then if you take derivative on the left side of the equation, you also have to take derivative on the right side of the equation. So in this case, we're going to get a big old 0. Derivative of a constant is 0. Okay. Now, collect all your dy dx's on one side, move everything else to the other, and solve this puppy. So I'm going to end up with 2x minus x dy dx minus y plus 2y dy dx equals 0. And I just need the dy dx's together. I need everything else on the other side. So what I'm going to do is move my 2x and my y over. Okay, so this is going to give me negative x dy dx plus 2y dy dx equals negative 2x plus y. Okay, and then factor out dy dx because it's in both terms here. Here it is right here, and here it is right here. So we can factor that out. So dy dx actually can come out here in front. Okay, and then it's going to be times negative x plus 2y. So when I'm working this guy out and I ask you what the derivative of this ellipse is, then we would say that dy dx, the derivative with respect of y with respect to x, is equal to, and then notice down here on the bottom, I've got dy times negative x plus 2y. Guess what? To get dy dx by itself, I divide both sides of the equation by that thing. So I'm going to end up with negative 2x plus y over negative x plus 2y. There's my derivative. And it's important to notice that you have x and y in here, which is why they gave us a specific coordinate with x and y in it. Okay, so if I want to know what the slope is of this guy, then I substitute in those values of x. So I'm going to have -2 times x plus y, and so my x is going to be -1, and my y is going to be 2. And then also on the bottom, -x plus 2y. So over -x plus 2y. Excuse me, goodness. So I'm going to just put in here a -1 and a 2. And so my slope is going to be 2 plus 2 over 1 plus 2, 4, which is going to be 4/5. All right, and as long as this is good, I know that my normal is going to be the opposite reciprocal. So if this is my slope, the tangent to my slope is going to be -5/4. Okay? And with those two things now, I can write the equation of the line. My line now is not going to be hard to do. Okay? It's going to be y minus the y coordinate, or y plus 1, equals the slope 4/5 times x plus 1. That should be y minus 2. And then for the normal line, I'll write the normal right up here. So we need a perpendicular slope. That's going to be my normal. And so the normal line then is going to be y minus 2, dadgummit, equals the normal now, which is -5/4 x plus 1. So that's how we can use these two things to find the derivative of an equation, and we can use it to solve out and find a slope of a tangent line and a slope of a normal. So it's really interesting the way all of this works out. And what we're going to find is if we were to draw a tangent line at this point of -1, 2, it's going to have a slope of 4/5, okay, and it's going to have a normal, a perpendicular line to that, of -5/4. It's really cool. Alright, so with implicit differentiation you can do some really amazingly cool things, and I really like this next problem that we're going to work out. I don't know why, I just think it's really cool how all the pieces fit together. So what we're going to do is we're going to look at the second derivative now of a function, and so we've got this function here. Let's see, get my colors going. Second derivative, that's what that little 2 up there means, okay? But now we've got 2x cubed minus 3x squared equals 8. So we're just going to start by taking the derivative of both sides. And if you'll look and pay attention here, you'll notice there's no multiplying going on. So we don't have to worry about product rule. There's no dividing going on, so there's no quotient rule. All we're going to do is take derivative. So 2, let's see, 2 times 3 is 6, so 6x squared minus 6y to the, and then 2 minus 1 is 1. So the derivative of y is going to be dy dx equals 0. Okay, so here's how we're going to start this guy out. Now we want to get dy dx all by itself, so I'm going to move 6x squared to the other side, so this gives me -6y dy dx equals 6x squared. And then I'm going to divide both sides by -6y. And so this gives me my first derivative, dy dx equals, and notice here the 6's go away, so this is just negative x squared over y. Okay? Pretty fun stuff. Pretty fun stuff. So what we're going to do is just rearrange this just a little bit because I don't want to have to do quotient rule all the time. And now that we're chain rule experts, check this out. I've actually got negative x squared times y to the negative 1. Now, this is not going to be too terrible to differentiate again. And so notice I've got dy dx, so I need the squared versions of those. So d squared y dx squared is, and then now I do have product rule, okay? I've got u and I've got v. Okay? So u is negative x squared, u prime is going to be negative 2x. And v prime is negative y dy dx. And this should actually be to the negative 2 power here, okay? So what's this going to look like then? It's going to look like u negative 2x, I'm sorry, negative x squared times v prime, and that's my negative y to the negative 2 dy dx plus v, which is y to the negative 1. Let me get the right color here. Times the derivative of u, which is negative 2x. So clean all this up just a little bit, and let's clean this up. We'll give it all this back to this kind of maroony color. So I've got x squared y to the negative 2 dy dx minus 2xy to the negative 1. Okay, doesn't look too bad, right? Like, it looks bearable here. Like, maybe we could do this. So how can we clean it up a little bit more, though? Because there's that dy dx running around in there. Well, remember way back when we discovered that dy dx is this guy right here. That's this step. So we just substitute that in down here for dy dx. So I've actually got, okay, let me see, let's give myself a little bit more room here. I've actually got x squared y to the negative 2 times now negative x squared y to the negative 1. Now I went with the all numerator portion of our derivative, okay? So nothing tricky, minus 2xy to the negative 1. So to kind of clean this guy up and bring it all home and make it pretty, I can add together exponents of bases that are the same, okay? And so to make this all clean and kosher, I'm going to write it back up here at the very top, okay? My answer is going to be negative x to the fourth over, and then negative y to the negative 2, y to the negative 1, that's y to the negative 3. And remember, y to the negative 3 is the same as this. Minus 2x over y. Okay, and that's what our answer looks like. And I don't know. I think this is really just a neat. I just think it's a neat problem. Couldn't tell you why I think it's a neat problem. I just think it's a neat problem, and I enjoy working ones out like this because you really have to pay attention and think and make sure that you're doing the right stuff. So double check all my signs in here. I think I'm okay. but you never know. Sometimes you get kind of lost in these problems a little bit. This may have to become a plus. I can't remember. But my teacher senses are tingling. But this is if not 100% correct, mostly correct. Okay, so if you can find that little whoopsie-do, please point it out to me. All right. The other one is you taking the derivative of a rational exponent. We have kind of done this in class already a little bit, but notice that that guy is not our normal looking exponent. Okay, so we're just going to take derivative of cosine x to the negative 1/5 power. I'm just going to look at it this way. I'm going to take the derivative of u to the negative 1/5 power, and I'm going to let u equal cosine x. So du dx is going to be negative sine x here, and the derivative of u is going to be negative 1/5 u to the negative 6/5 times du dx. And so when I simplify this guy out, I'm just going to have negative 1/5 times u, okay, to the negative 6/5 power, and then times the du dx part, which is negative sine x. So how does all this work out? Well, you can't be finished here. Go ahead and multiply these two things together. Negative times a negative is positive, so I'm going to end up with 1/5 times cosine of x to the negative 6/5 sine x. And all I wanted to show you with this example was it doesn't matter what your exponent is. It could be a pi, it could be square root of 2, it could be whatever you can imagine. You're just going to take whatever that exponent is, move it to the front so that you can multiply and just subtract 1. So just a real quick, crazy looking example without trig. Let's say I had 2 to the pi power. Okay, the derivative of this is pi times 2 to the pi minus 1. Okay, and that's how we would write it. So that's all that I want you to see with this guy. And we've worked some problems out like this. They're kind of fun too, but that's how you use implicit differentiation. It's really a really cool thing to have in your back pocket. It now opens up the whole world for us with derivatives. There's nothing else that we need to learn except a couple more little rules as far as dealing with like logarithms and exponentials and things like that. But we've been given the tools to take the derivative of just about everything that we come across.